Section 8.3, Evaluating Logarithms. Exponential equations can be solved using one of these three methods. You can use trial and error, graphing, or you can use logarithms to solve exponential equations. The first thing that we're going to look at is the idea of solving exponential equations using trial and error. So if we take a look at this example right here, 320 is equal to 5 times 2 to the power of 4x minus 3. The trouble with this equation is that the x appears in the exponent. So this is something a little different than what we've seen in past years where we could just rearrange and solve for x. The x is an exponent, so we need to get the x somehow out of the exponent or create an equation by which we can evaluate x. The first thing I'm going to do here is I'm going to take both, I'm going to rewrite this. So 320 is equal to 5 times 2 to the power of 4x minus 8. And I'm going to divide both sides by 5. And that will eliminate the 5 on the right hand side. 320 divided by 5 is 64. So 64 is equal to 2 to the power of 4x minus 8. Well, this is helpful because 64 is a perfect power of 2. Right? So 64 can just be written as 2 to the power of 6. And then we have equal to 2 to the power of 4x minus 8. So this is what we call establishing a common base. So we establish the common base of 2. So that means 2 to the power of 6 is equal to the same thing as 2 to the power of some number. But if these two numbers are equal, then that means that this exponent here must be equal to that exponent there. So I write, therefore, 6 must be equal to 4x minus 8. And now I can solve algebraically as I know how to do, which is 6 plus 8 is equal to 4x. 14 is equal to 4x, and then divide both sides by 4, which allows us to say, therefore, x is equal to 7 over 2, right? 14 over 4 just reduces to 7 over 2, not 17, 7 over 2. All right, solving exponential equations by graphing. Approximate the value of x for 50 is equal to 2x using the graph to one decimal place. So we're going to take this graph right here. And this is our graph for y is equal to 2x. And we need to find the exponent on 2 that would cause y to equal to 50, right? So basically I have this graph right here, y is equal to 2x. And instead of y, I need 50. So 50 is equal to 2x. So my y value is 50. So I look at 50, I go across, I find that value on the curve, and then I go down to the x-axis. That will give me the exponent on 2 that would cause the y value to be 50. And so therefore, if I read this off the graph, I say that therefore x is approximately equal to, I would say, about 5.6. Okay. You could also say, well, is it 5.7? So you could try 5.7, but you would find that you get a closer answer at 5.6. That is, 2 to the 5.6 is closer to 50 than 2 to the 5.7. So this is what we choose. We choose x is equal to 2 to the power of 5.6. So again, we have the graph y is equal to 2x. We set y equal to 50, go along our graph, and estimate or approximate the value of x. So that's another way of solving an exponential equation, right? In this case, 50 is not a perfect power of 2, so we can use a graph to approximate the value of x. Now you can also solve exponential equations using logarithms. So right here we have basically a rational expression. We've got a rational equation. 1875 over 7 is equal to 3 times 5 to the power of negative bracket 2x minus 3 close bracket all over 7. So you might notice that the first thing we're going to do is we're going to want to clear this fraction, and we're going to get rid of this 7 just by multiplying both sides by 7, and that will help eliminate the fractions here. Let me just redo this bracket here. Okay. So by multiplying both sides by 7, I can effectively cancel the 7s here and here and here. And then I have 1875 is equal to 3 times 5 to the power of negative bracket 2x minus 3 close bracket. Okay, again, I'm going to divide by 3 to get rid of this coefficient here. Okay, and I should get 625 on the left side is equal to 5 to the power of negative 2x minus 3. All right, so what we're going to do here is, instead of changing this to a power of 5, what I could do is I could take the logarithm base 5 of both sides. So the logarithm base 5, 625, is equal to logarithm base 5 times 5 negative 2x minus 3. Well, you should recall that this right here will actually just return negative 2x minus 3. And the reason for that is as follows. I'll give you an example that might be a little easier to understand. If I said logarithm 2 to the power of 6 base 2, well, that's basically saying, okay, well, what is the exponent on 2 to the power of 6? Or sorry, what's the exponent on 2 that causes it to be equal to 2 to the power of 6? Well, that's self-evident, right? That should be 6, right? So what's the exponent on 2? What exponent on 2 causes it to be equal to 2 to the power of 6? Well, obviously, that's 6. So what exponent on 5 causes it to be equal to 5 to the power of negative 2x minus 3? So here, 5 to what exponent is equal to 5 to the negative 2x minus 3? Well, we can see that this expression right here is the exponent. Now, if we look over here, 5 to what power or what exponent gives us 625? Well, that's 4. And so now I can solve regularly by isolating and solving for x. So I'll distribute the negative. Okay. And then I can go and solve, and eventually I get x is equal to negative 1/2. Okay, I just put dot 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 here because I don't think I need to go through all the steps in solving for x here. That's a grade 9 concept. All right. Now, if you're not familiar with this stuff right here, which is, like, well, how did you go from log 5 to the negative 2x minus 3 base 5, right? All of this right here, these ideas were covered on page 3 of this handout. So you can take a look at that right there. We looked at some of the general rules of logarithm on page 3. So this is just a repeat of material you've seen before. If we look at just evaluating logarithms using the definitions of logarithms, okay, remember that a logarithm will return the value of the exponent for the given base. Okay, again, all this says right here, logarithm 216 base 6. What I'm looking for, what this returns, is the exponent on 6. So 6 to what exponent gives you 216? Well, the answer there is 3. So logarithm 216 base 6 is equal to 3. Let's look at this next problem right here. Logarithm 1 over 8 base 2. So again, I'm saying 2 to what exponent would give me 1 over 8? Okay, well, let's explore 1 over 8. 1 over 8 is the same thing as saying 1 over 2 to the power of 3. And 1 over 2 to the power of 3 is just the same thing as saying 2 to the negative 3, right? Because a negative exponent causes you to take the reciprocal, right? A negative exponent produces a reciprocal. So 2 to the negative 3 is just 1 over 2 to the 3. So effectively, 2 to what power gives me 1 over 8? Well, 2 to the negative 3 gives me 1 over 8. If we look at the next question right here, logarithm negative 27 base 3. So 3 to what power would give me negative 27? Well, hopefully that should cause some alarm for you, because positive 3 raised to no exponent can give you a negative number. 3 to raise to any exponent here will always give you a positive number. It might give you a fraction, but it will always produce a positive number. So therefore, this right here does not exist. There is no exponent on 3 that would cause you to get negative 27. Okay, so no, we can write that out. No exponent on 3 produces negative 27. Okay, for this next question right here, again, we are thinking 4 to what power produces the cube root of 16? Well, this stuff right here causes us to recall what we learned in grade 10, or rather grade 11, is that 16, the cube root of 16 is the same thing as saying 16 raised to the 1 over 3. And 16 is just 4 squared to the 1 over 3. So that's basically 4 to the power of 2 over 3. So 4 raised to what power gives you a cube root of 16? Well, that's equal to 2 over 3. Looking at this one right here, logarithm of 3 base 81. So again, 81 to what power would give you 3? Okay. So if we think about that, if we took 81, right? If we took the 4th root of 81, we would get 3. So how do we write the 4th root as an exponent? Well, 81 to the power of 1 over 4 is the 4th root of 81, and that should be equal to 3. So what exponent on 81 produces 3? Well, 81 to the power of 1 over 4 produces 3. So the answer there is 1 over 4. In this question, log 1 base 6, 6 to what power gives you 1? Well, 6 to the power of 0 gives you 1. Okay, this question again is very similar to what we just looked at up here. Okay, what we're saying here is 10 to what power is equal to 10 to the negative 2. Well, again, that should be pretty self-evident, right? 10 to the negative 2 gives you 10 to the negative 2. So this answer is very simply negative 2. Okay, in this question right here, we have to think a little carefully. So we are finding the exponent on 3 that causes this to equal x. So the exponent on 3 that produces x. Okay, so if we find that exponent, right? So that means logarithm x base 3 is equal to some exponent y, right? So that means 3 to the power of y equals x, based on this right there, right? 3 to the power of y gives you x. That's what this means, right? Okay. So then if I write 3 log x base 3, that's the same thing as saying, well, I know that log x base 3 is equal to some exponent y, right? So that means 3 to the y, right? But we already said that 3 to the y equals x, so 3 to the y just equals x. So log x base 3 as an exponent of 3 simply returns x again, right? Just to review, I'm just going to look at the exponent alone. Log x base 3 equals some exponent, right? And this means 3 to that exponent produces x. So when I go and I evaluate this, log x base 3, I can just say that that's equal to y. So 3 to the y. But I know 3 to the y produces x. So that means 3 to the y just gives me x. Evaluating a logarithm using a graph. So this right here is the graph of y is equal to logarithm logarithm x base 5. So logarithm x base 5. So logarithm x base 5, what we're going to do here is I have this graph right here, log x base 5. And now what I need to find is log 75 base 5. So y is equal to log 75 base 5. So that, base 5. So that means, therefore, x is equal to 75. So I find 75 along here. Okay. And I go about here, I think. And then I go across and I find what is the y value there. So it looks like I'm going to have to estimate. And I could do two things. So I could say that y is equal to, it could be equal to 2.6, or y is approximately equal to 2.7, or y is approximately equal to 2.8. Okay, well I can test this out. 5 to the power of 2.6 is equal to 65.7. That's not very close to 75, so we're not going to take that one. 5 to the power of 2.7 is equal to 77.1. Okay, that's actually pretty close to 75. Then we say 5 to the power of 2.8 is approximately equal to 90.6. So I won't take this one, I'll take this one right here. So therefore, y is equal to 2.7, or logarithm 75 base 5 is equal to 2.7 approximately. Okay, so again, instead of x, we inputted the 75. We found the approximate y value, and we had a range of them. We picked the one that brings us closest to 75. And so we chose 2.7. Okay, your calculator has a log button. However, it's the common logarithm, so it's like logarithm base 10. You can use the following formula, which will be proven later, to determine the logarithm of a number you cannot intuitively determine. So for example, you can use your calculator to determine this. Log 194,481 base 21. Okay, we can actually just input that this way. So log base 21, 194,481. We can actually just use our calculator to say, okay, logarithm x, that's x right there, right? 194,481 all over logarithm of that base, 21. And note here, I'm not writing what the base is because it's assumed that it's 10, right? That's the log button on your calculator. It's already base 10. And so we can input that into our calculator and we can get an approximation. I think this actually is equal to 4. So we just write 4 right there. Okay, so these are all ways of calculating both logarithms and solving exponential equation. Just to quickly go over it again, the first way we learned is establishing a common base and then making the exponents equal to each other. We can use a graph to solve an exponential equation. We can use a logarithm to solve an exponential equation. And then we can evaluate the various logarithms using the properties of logarithms. And then we can also evaluate a logarithm using a graph as well, or the common logarithm. Okay, homework is listed there. Thanks for watching.